Hey, check it out, a package came from SparkFun. What is it? It's the Raspberry Pi 400 computer and packing material. Kind of like that it's called the 400. It reminds me of the Atari 400, even though that thing was a piece of crap. I had the 800. Yeah, a nice little box. Oh, that's kind of cute. The box represents, well, at least two sides of the computer, the front and the back. That's neat. So, a couple reasons that I got this. One was because I wanted it. Another reason was, I think the newest Pi I have is like a A3 Plus, or the Pi 3A Plus. So I actually don't have any Pi 4s at all at the moment, so this is a Pi 4, that's good. Oh yeah. I wonder how much science goes into having a product in the face of a box like that. You know, like with no padding whatsoever. Like how much damage it can take. I think they have machines that actually simulate all that. So, yeah, it's pretty much right here. It's kind of thinner than I expected. It looks like it has an SD card included, so I assume this thing just boots right up to Raspbian. Looks like they've got the header output right there. Looks like the standard size header, I believe, like from the Pi 2. USB 3.0? Interesting. Then, oh, Ethernet. Well, yeah, I guess it had before. Kensington lock? Very fancy. And for all of you fans out there, there it is, USB-C. USB-C can provide much more power than USB. The USBs before it. Ooh. Oh, good, because I really needed a card adapter. The official mouse, which I assume isn't going to be that great. Yeah, what's with that trend now of like not including these power bricks? You know, like there's all these things where it's like, oh yeah, it's your mini Sega Genesis console and it runs off mini USB or micro USB, but it doesn't have a wall wart. I guess we all have those wall warts and they're like trying to be green, but they're just trying to save money. But yeah, this actually is hardwired. Interesting. 5.1 volts at 3 amps. Okay, so yeah, that is a little higher than you'd probably want to. Well, actually, that's a lot higher than you would do with a regular USB port. And you use like a USB micro fast charger, would have been about 2 amps. So, oh, there's like a book. Oh, look, yeah, there's a book. That's cool. The official Raspberry Pi Beginner's Guide, how to use your new computer. Take a look. Ooh, it's a color. It's in a book, a reading rainbow. I can do anything except find a girlfriend on Star Trek Next Generation. What about that part where Data wants to get a girlfriend and the first person he goes to for advice is Geordi? I mean, I know Geordi's his best friend. I mean, don't tell any of the Next Gen movie writers, but newsflash, Data's best friend is not Picard, it's Geordi. Picard's best friend is Beverly Crusher. 247 pages. A lot of kids probably are like, what's a book? I wonder if kids like look at a book and try to touch it, you know, like, oh, why won't this click button not work? What is, oh, we've got a, looks like micro to regular HDMI cable adapter. Got the Raspberry Pi 400 set up here. Does this thing turn on by inserting the power port? Is it following the British tradition of the Sinclair ZX Spectrum? I guess the ZX81 did that as well. Yeah, one comment I would make, well, first of all, I know I'm already going to hate this mouse, so I'm not going to use it. The USB ports are on the left-hand side, and the cord isn't very long, which means this mouse actually is going to be less functional for right-handed people, which is, what, 90% of the world. So that's kind of weird. They don't have, like, a longer mouse cord. Maybe they wanted to make it kind of, like, cute and compact. Oh boy, I can install the History Channel app to this TV and watch historic things like Ancient Aliens and The Curse of Oak Island. Oh, that fired right up. Okay, I guess you turn it on by plugging in the USB power source. It is like the ZX Spectrum. Oh, I'm sorry. ZX Spectrum, Pico, Pico, blah, blah, blah. I tried this wireless mouse and it's really laggy. That's kind of weird. I don't know why it's having such trouble. Well, I could always try another wireless mouse. I have many of them. I mean, I like how this computer's built into the keyboard. It kind of reminds me of, like, you know, like the 80s. It's weird that I can only see 2 wireless networks. All of my neighbors should have one up. Oh no. Don't look at my network password. This keyboard is pretty serviceable. There's not a ton of throw to the keys, but it's all right. I mean, it kind of reminds me of like a laptop. Oh, we might need to update your software. It could take a while. Okay, so I'm going to compare the setup time for the Pico, Micro. You say micro, you don't see micro. Yeah? Whatever that thing is. I'm going to plug it in to the Pi 400 and we'll see how setting it up in C compares to Windows. I noticed this has Thani included in the application, so Python development would be easier than falling off a log. But C, I'm sure, is still a few extra steps. Let's find out. Sit adrift on memory bliss with you. All right, so there's the Pi hooked up. I assume this is going to show up as a mass storage device. Where is... Oh, there we go. Open a file manager. There we go. Okay, yeah, so it's under media. So yeah, it's like any removable device. Let's see what's in there. Raspberry Pi 2. All right, well, it gives you the link. So let's see. Getting started with MicroPython. It's like a baby snake. Okay, download the file. Okay. Where did the file go to? Oh, it's Chrome. Oh, Chromium. Yes. I assume this went to like the way. I can't open that file. Show me where it is. Oh, under downloads. I guess that makes sense. Okay, let's open a second folder. I feel like that episode of The Office where Michael Scott was trying to use PowerPoint. He's like, PowerPoint. And, well, it looks like this is going to update. Gave me the unstable version? Oh, what the heck. Let's drag it over. Wait, it should go right here, I think. And I believe Thani should be under programming. So we go to the options and we go to interpreter. We actually don't have an option here for the MicroPython on the Pi Pico, so I guess we're going to have to download that. We must need the newest version of Thani in order to have that support, I guess, because, yeah, the Raspberry Pi 400 does predate the Pico? You know, it's like how I say multimeter instead of multimeter, right? Like, you don't say altimeter for an airplane, you say altimeter. Potato, potato, let's call the whole thing off. Wow, almost a gig of updates. Yeah, this is so much better than Windows. Oh, shots fired. Oh, but I can play modern video games on Windows. Oh, ballistics launched. Okay, well, I'm still updating Linux in the background, but looking at the Getting Started guide, we have the SDK setup, the Getting Started documentation. That's what I used earlier. However, if you're intending to develop for the Pico on the Raspberry Pi, then you can set it up using the setup script from the command line. Oh, so I guess we're going to have to save this and run it. Well, in the meantime, the quick brown fox jumped over the lazy dogs. Yeah, not too bad. Let me try that again. What was that? Mabel Bacon teaches typing? Mabel Bacon. I'm Mabel Bacon. The quick brown fox jumped over the lazy dogs. I keep missing the same keys. In my younger and more impressionable days, my father gave me some advice which I've been turning over in my head ever since. Also not a command. Yeah, not a bad keyboard, you know, for what it is. Oh, cool. H-top is built in. All right, we can see all the 4 cores. Pretty neat. Oh, wow, this thing has 4 gigs of RAM. That is totally respectable. Well, Chromium's taking up about half of the CPU. Oh, Chrome. You are a fickle mistress. Oh, while trying to function out of H-top, I noticed there is a power symbol on F10. So I wonder if that's a secondary function, because there's a function key here. Well, let's see. The function key is red. All right, so that means that would set the secondary function of each of these keys, including system request and insert. All right, Linux is updated. Let's see if it also updated Thani. Where is that here? Detect automatically. There we go, we're connected. All right, well, aside from me having to make sure the Pi 400 was up to date, that was, you know, pretty much the same level of difficulty as Windows. You know, you just basically install... Well, actually, no, Thani comes built in with newer versions of the Raspberry Pi OS, so that makes it easier than Windows. You're no longer updating, you don't really have an excuse to be slow. Let's see. There we go. Did my alias take? Ah, good, it did. All right, let's run that script. Sudo bang bang. The heck? Oh, it's not executable. Boom, 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 boom. There we go. Pseudo. What was it Felix had? The pseudo sergeant? And I was like, Felix, it makes it sound like you're not a real sergeant. All right, well, the setup script should do all of the toolchain automatically. So I guess we can just jump to the part where we're using it. I'm going to download the same file here. All right, so apparently we've done this, so we should be able to jump right to blinking and LED and see. Then, assuming you clone the Pico SDK and Pico examples repositories in the same directory side by side, set the path. No, we had to do all this stuff? I wonder if this is making a Pico examples folder for us, just like on Windows. I'll wait for the process to complete before I continue. Oh, I might add, this is a 4K TV, and it looks like the Raspberry Pi 400 has no problems outputting 4K. It's almost kind of like too small, like these windows. I mean, I can read them, but I don't know. And I tried to increase the text size, but apparently that's not sticky. So that's my impression of the YouTube comments. Oh, look at your torn up nails, Ben. Actually, my thumbs are looking quite svelte today. I googled it. Apparently, if you hold this power button down for 2 seconds, that will turn off the machine, and then you can also tap it to turn the machine back on. So, sorry, Clive Sinclair, your legacy of no power switches is over. Although, something weird, like if you look at, you have insert and delete here, and so insert should be under the red function key, but it doesn't seem to work. So, also page up, page down, home, and also have those red function keys as well. I would say some feedback, as someone who's about 50% colorblind, the red doesn't look that much different than the black, so maybe they could have made that a little bit more distinct. The script completed. Let's see, where did it... Documents, where did it put all those files? Oh, looks like I put them in the same folder the script executed from. Pico SDK. I'm not sure if that's really where I want it to be. You know, so far I'm not entirely convinced this is that much easier than doing it on Windows. I mean, there's that easy script that apparently did everything for us, but I don't know. I mean, I noticed this also has Visual Studio Code built into the operating system, so maybe that'll help. I don't know. All that for a drop of blood. I'm going to try redoing the configure script in the folder where I actually want all the Pico files to be. I think I was just, you know, flying too close to the sun. So this is probably going to take another 10 minutes. Even on the Pi, it's like, it's just so much easier just to download the bloated Arduino, 400 megs, unzip it, slap it on the desktop, boom, it works. I completely updated Raspbian, so it's up to date. So these are all the steps I'm having to take, even with a completely up to date Raspberry Pi OS. Well, and part of my motivation for getting this was I wanted to have a handy ARM Linux box. I mean, I had actually the most modern Raspberry Pi I have is like a Raspberry Pi 3A Plus in one of my little portable game consoles. So I didn't have any Raspberry Pi 4, so now I do. Yeah, I could probably make a thing where the keyboard like hides under here. I mean, well, it's a computer, not just a keyboard. That'd be kind of cool, right? It's like, you are now in Pi mode. All right, I went in and I did the script over again where I actually wanted it to be. Let's see if we can make blink this time. It worked! Yay! Alright, so there's Blink UF2. So I guess the moral of the story is if you use the Pico setup script, make sure you execute it where you want your Pico SDK files to be. There were fewer steps than Windows, but it still took probably about 30 minutes to set all that up. As opposed to Arduino, which is however long it takes you to download and uncompress the zip file of it. Well, I guess let's try making our own C file and see if that's a big improvement. Just because I'm using a Raspberry Pi to program this, that doesn't change the fact that I still have to unplug it and plug it back in while holding the button in order to enter programming mode, which is still, you know, less convenient than most microcontrollers that I can think of. All right, I dragged the file over to the Pi Pico, and sure enough, it is blinking. Yay! I just read through the section about the SWD port. That's the programming port down here on the bottom, but unless I'm mistaken, it seems like that's only used for debugging, not programming. But yeah, there's that run pin on the Raspberry Pi Pico, and I believe that is the same as reset. So I'm pretty sure you need reset in order to program with SWD. A regular ARM microcontroller, you'd program it over SWD. You could program it and then also immediately go into debug mode. This seems a little overly complicated. Here we go, using Visual Studio Code. Now that's the same thing that we did on the Windows version. I notice Visual Studio Code itself is already installed, but looks like we need to install these additional things as well. Looks like that's already been installed. Well, I'll double check and then we will try to, you know, do this using code. Wait, and I once again have to set a path and then execute code from a terminal? Oh, it loaded fast. I'll give it that. The soldiers' uniforms were very realistic. Should be open folder. Yeah, there we go. We're going to go to Pico examples. Very well. We're going to open the entire folder. Okay. Open entire folder. Visual Studio Code uses folders instead of projects. Alright, yep, okay, so there's all the examples there. And now I'm letting Visual Studio Code compile it. I mean, I'm pretty sure it's still going through CMake and make. You know, I'm not like a Linuxologist, but I know you can go into a terminal and you can, like, you know, write something in GCC pretty easily. and it just works. So I kind of wish, maybe in the future they will have this built into Raspberry Pi distributions. I don't know. I'm going to see if I can just build Blink. Let's see. So let's see if it actually works. Let's speed up the rate of Blink. Okay, save it. Build Blink. Okay, well that didn't take long, which makes sense. So now this, I mean, I do not like this part about it. So I hold down the button, I remove the power, then I give the power back, I release the button, and now it's in bootloader mode. Like what a lot of those systems do is they'll use, the programmer will send a baud rate change over the USB port, and that will be interpreted as a software reset signal. Now I guess you could say, oh, well, you know, you can't really do that if, you know, unless you have a USB, unless you're using the device as a USB, and I guess that's true. Alright, so where were we? We were Pico. Let's just drill down to the bottom of the planet Earth. What? How did it get bounced back? Alright, let's see if that makes a difference. Whoop. And yes, there we go. We now have the high-speed blinking. I would say the setup time is about equal to Windows. The only difference is instead of having to like install 5 different things, which honestly goes a lot faster on a large computer, it's still, you know, a long process. You have to make sure that your Raspberry Pi or your, you know, your operating system is up to date. That didn't really seem all that much easier than setting it up on Windows. Yeah. I mean, I think part of the issue is, you know, if you have something like, oh, like, you know, like an Adafruit Metro M4 or something from STM or some new chip from Microchip or Atmel, they're already, you know, tool change, all, you know, set up for that. I mean, granted, yeah, this isn't ultimately an ARM chip, but it's a custom new chip. And maybe that is why setting up for it is a little bit more complicated, because there isn't any existing infrastructure. Versus, you know, if, let's say there's a new ARM chip that comes out for Atmel, you might have to download a new package in Atmel Studio, which will be automatic. Other than that, it should basically just work. You know, a USB port, you know, it's not rated for infinite cycles, right? So, and the fact that it's making it so you have to unplug, physically unplug it to cycle the programming is, I don't know, it's kind of weird. I'm a Linux expert, like I'm like an expert marathon runner. I can like walk down the street and not fall into the road, and that's about it. Oh yeah, there we go. Okay, so this was set in bash rc export Pico SDK path. Cool. All right, well that's not too bad. And I guess what we should try next is making a program from scratch, right? Let's see. This, I know this had the CMake list thing. Add executable, blink, pull our Pico standard library in. Okay, target link library. Create map, extra outputs. These instructions do cover making a program from scratch. We will need to copy the Pico SDK, import CMake, and then CMake list to use as a template. Yeah, so why don't we go ahead and do that. So we'll copy those two. We'll go back. We want to be parallel in the structure to Pico SDK. So what can we call this? Let's call this Possums. Alright, so we'll go into Possums and paste those files, and then we'll also make Possums C. Oh, you should have done that from the terminal with touch. Alright, so let's go into Pico, Micro, Pico, Micro, Nano, Picro, Micro, Picro. Oh, I can just hear the hair being torn from people's heads. Alright, so CD, make directory build. I should probably spell that right. So we're going to go into build, and then we're going to CMake the folder above build. So CMake ... Function missing ending. Oh, crap! I made a typo. Oh, I see what I did. I did a curly bird instead of a parentheses. Oops. Let's see if that works. Okay, that seemed to work. It's called Possum C, not Test C. I'm being very testy with my code. I don't really trust this keyboard to not look at it when I'm typing. We now have a make file. Come on. Come on, little raptor. Come on to that egg. This is all just to compile that little C program. Okay, looks like we got our file. All right, I'm going to cycle the Raspberry Pi again. I really wish it had just a... Well, actually, there is that run button. I wonder if we could hook up a button to that to make a reset button. I should try that. Well, let's test this first. All right, so there's our... Drag it over. And, yep, she worked. See, that actually seems a lot more straightforward than doing it in visual code. Nanopos. Oh, look at me. I'm a terminal jockey. Every year I go to the terminal jockey jock fest. I wonder if I can do function insert here. No, that might maybe go to a function. Yeah, it's weird. The insert button doesn't seem very useful in a lot of aspects of Linux, or at least on this Raspberry Pi. Let's give this a shot. Okay, so I'm going to plug it in, and it should just do the previous code. There's the run pin. I believe it's active high. Oh, I can still see the LED blinking through the PCB. So let's see what happens if we take it low. Okay, that does reset it. Run to the hills. Run for your life. Okay, so let's see if this works. All right, let's hold it into reset. Hold the button, release reset, and it worked. See, we've got the mass storage device. All right, cool. Well, you know what? I think I should just add a button to this. Got this large tack switch here. I don't know, I just grabbed a random Surface one from my collection. I don't really see myself using that debug port. And if I did, I can always just, you know, solder something through. So let's get our ground from there. I don't think I even need to glue the switch, you know, the solder should hold it. And let's see, run is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's the way you're making me feel. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh yeah, you can see there's a little pull-up resistor, I assume, right next to it. That makes sense. Can you feel the love tonight? Da, 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 da. Shining new era, it's tiptoeing nearer. My family visited and we watched that last night on Disney Plus. The original, of course. They're not going to watch any remake nonsense on my TV. Oh no, I've covered up the Raspberry Pi logo. For shame. Now you should be able to just go boop like that. Okay, I plugged it back in. It's in blink mode, so reset, hold that, reset, that, and then it should come up in Linux. There it is. Cool. Why couldn't they just have added an extra tack switch to this? Although tack switches are actually kind of expensive, so that's probably why they didn't, but you know, like just 2 switches, right? That would give you so many more options. It's kind of ironic, this Pi on this screen is running at a higher resolution than my big computer upstairs. That's only 1440p. And then, yeah, even then you got your main folder, then you got the build folder under that, and then you got to drag it over, and okay, yeah, that updated correctly again, so I guess I only have to make the CMake configuration once. Also, it's kind of dark in here because I turned off one of the overhead lights so it wouldn't reflect in this TV. I don't know, just clicking and dragging a file, you know, like a UF2 file, it just seems kind of cumbersome. It's easy, but you know, if you're actually developing something and changing things rapidly, I think it would get a little annoying. I suppose what I should do is write the same automatic cat laser code in C. So I'm going to need a random number generator and a PWM generator. So how would this go? Let's do this. Let's take those files, copy them, go up one, make a new folder, call it, surprise, surprise, laser cats. Fellas, you've got laser cats. Those are illegal. Do the right thing. And then we'll call this laser, just laser. Light amplification from the stimulated emission of radiation. You know, I think I was arguing with Pat, the NES punk, and he's like, oh man, you don't say SNES, you say SNES. And I was thinking, yeah, that's kind of dumb because there's all sorts of acronyms that we say as words like laser, scuba, radar, JPEG, MPEG, GIF. I mean, most of them actually, right? Yeah, so I just think it's kind of dumb. SNES. That takes too long to say. SNES. All right, so I just copied the possum thing and called it laser. Yeah, all right. All right, so right now laser is just gonna blink the LED as before. So let's go into the build folder and let's open a terminal here. Come on, there we go. I've been present for the birth of every little creature on this island. CMake above. Okay. Cool, and then make. Oh, I bet it's taking longer the first time because it's compiling everything that is related to laser, but then when you recompile it, it only has to recompile what changed in the laser C file. But if I'm incorrect with that assessment, be sure to... Wait, I don't even have to ask you to leave a comment below because I know you will. You know, it is fun correcting people on YouTube. I do it as well. I'm Bane. You think laser cuts will save you? All right, that worked. Cool. Now I just need to find the libraries in order to reproduce the servo project. All right, I grabbed a PWM example from the examples folder. I made it. Let's see if it'll take. Flashing it over, and nothing is on the scope. Well, that's lame. Maybe I did something wrong. I compiled, but it's not working like it's supposed to. All right, PWM example is set up, and we are getting a waveform out of it. Cool, so now I need to figure out how to set the correct period that we need for servo motors. So I've got PWM set rep, slice num, which is what PWM bank we're on, and then 1000. I can just get an idea of what the default is by setting 1 to 1 and the other one to 750. I'm guessing it's about 64 megahertz that this counts at. I will say this seems to be the easiest way to do it in C, basically just to have the C file open in some other program and then just continually run make in your build folder. Oh, okay. All right, so that's 12.5 kilohertz. So I went from 1,000 to 10,000. So that does appear to affect the count. Interesting. I think I could probably divide it with what I have right now. Yeah, I think we need to divide the clock by 256 to get into the range that we want. Just kind of guessing. So here I can make this while I reset this. And then our window should come up. Oh, there's our window. Okay. Okay. Oh, that gets us pretty close. 49.01 hertz. I think I can work with this. Okay, so we're dividing the clock by 256. Then we're doing a period of 9,800 slices, and that gets us pretty much right on 50 hertz. Okay, now we can use math, sir. All right, I'm just going to convert the Python. Void set servo, angle X, angle Y. Then down here, we'll enable it, and then we'll set it. Set servo. Actually, let's go 0, 0. Yeah, because we're going to be looking for the base width, which is 1 megahertz. I'm sorry, 1 millisecond pulse width. So it's 1 millisecond to 2 milliseconds. I have all these calculators laying around. 9,800 divided by 50. 196 ticks per millisecond. Oh, that works out pretty good. All right, so I've just commented out the multiplication part. So we'll have a base of 196 ticks, which should get us a 1 millisecond initial pulse, which is what we want, and then we can go over that to get the servo positions. Now that's creating a pulse of 4 milliseconds, so I'll divide the divider by 4. Yeah. I'll go from 256 to 64, which means the same amount of ticks will be reduced, since we'll have a higher number. So we're not dividing the clock by as much. We're only divided by 64 instead of 256. So it'll be 4 times faster, which means 196 ticks will go 4 times faster, which should be 1 millisecond. And there we go, 1 millisecond pulse. Okay, cool. Actually, if we wanted to make sure we had enough granularity, we could divide the clock by less. So we could divide the clock by 32, which means we would double the number of ticks. But that would be good, because if we have 196 ticks in 1 millisecond of space, that means we've only got about 1.05 degrees per tick. So if we have a higher number, that'll give us better granularity. Well, mostly we won't have to worry about the rounding errors from the multiplication. I had to adjust some more math in order to get the timing right, but I think I got it now. Let's see if the servo does what it's supposed to. There we go. 90-90. Nice. It's now running in C. I found a random number function. It's part of the standard library, so that seems to be working. Yeah, there's also a sleep milliseconds function. So yeah, I basically just ported the code over from Python into C. I'll go over that in more detail using an actual screen capture, which I'm sure you'll appreciate. And then we'll see how Bud likes it hooked up in the kitchen again. Bud is like, I don't care what language it is, as long as I can chase it. Okay, it's time to stop torturing you with a camera pointed at a screen. Here's a proper screen capture. Okay, so the CMake lists text file. This is important. So this has to reside next to your C file. So we're including CMake and the Pico SDK. Project, you can call this whatever you want. Doesn't actually have to match the name of the folder or the C file. But the executable, you have to actually say laser and then laser C. Add extra outputs. That's going to say, oh, we're going to make, the UF2 file. Laser, and then target link libraries. You have the name of your C file and then everything you're using. So the standard library, PWM, and ADC. All right, so the main C file itself, we're also including standard PWM and ADC. I don't really care for how it, here it says hardware underscore PWM, hardware underscore ADC, whereas here it's, a more straightforward format. All right, so here's set servo. So we have a base of 1953 ticks to make 1 millisecond, and then it's 10.85 ticks per degree. So we basically take the angle input, we multiply it by that, and we add it to that, and that's actually what we set the PWM channel to. It's interesting, yeah, so the PWM channels on the Pico Pi, there's 2 channels per PWM slice, and they go to 2 different pins. That's, well, actually, that's not entirely unusual. I've seen that before, where you can have multiple timers that have the same time base on other ARM chips. Get random. There is actually a function called rand, so I'm just doing a modulus divide to return a certain range. Laser flash, you basically give it a 1 or a 0, and then it basically, this time, oh, it's different. The lasers blink, left, right. They blink in inverse of each other. Target does basically the same thing. We have a random speed, then we try to achieve the target, and then we sleep for the speed. Basically, that's how long we sleep is how slow it goes or how fast it goes. And our main, we have all our inits, so we have these 2, which are used for the 2 lasers. Well, technically it controls the transistor. Then we set these functions to PWM. Slice number basically gets an index based off what pin you're at. Clock divider, I went with 64. Yeah, what is the clock speed on this? I can't remember. It was like 160 megahertz. So this would be the main CPU clock divided by 64, and that's what's feeding the PWM timer thing. It's doing 39,060 ticks or clocks before it repeats. So that's how I dialed in the duty cycle to get the duty cycle to get the 50 hertz that we need. Also ADC. ADC is pretty simple. You select input. I think there's only 4 ADCs on this chip, which is pretty low. So we're just going to go with 0, which is attached to GPIO 26. And then we basically center our servos to begin. And the code works pretty much the same as before. We set a random target, and then the servo moves from where it is to where it's targeted to go. Then we flash a laser a random number of times, anywhere from 4 to 8 flashes. Then we make sure the laser stays on. We sleep for a random amount of time. Then I added this. It flashes again before it moves, and then it goes back here. So yeah, that's our C code. So we converted from Python over to C. Then we compiled it on the Raspberry Pi. So let's set it up in the kitchen.
Get it, bud! It's not using an interpreted language! Get it!
Oh, are you still tired out from my family visiting? They really put you through the ringer, didn't they?
Get it, bud! It's behind you! They came from behind! It's to your left!
I think Bud's tired out from my family visiting. Well, anyway, there you go. Converted the automatic cat laser to C and developed it entirely with the Raspberry Pi 400. And yeah, it is more straightforward, although still probably more steps than it needs to be. But I'm sure that'll be improved in the future. Bud, did they make you all tired? Oh, poor Bud. so much petting and love last night from my niece and my sister. Bud just, he's all pooped out. Now he's gonna go eat his sausage. Big fat cat, belly rub. Big fat cat, belly rub. Rub, 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 rub your belly. Ah! So flashing the Pi Pico in C on the Raspberry Pi. Quick overview, blah, 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 blah. There's all this then. Got you suckers. So you're gonna wanna download the setup script, which is pretty easy. It's gonna be a shell script. And then place that where you want to do your development in your directory structure, because not only is it going to copy all the files there, it's also going to have a lot of the paths pointed there. Once you've done that, you'll create your project folder. Let's say it's a Laser Cats. Make sure your project folder is in the same directory as the Pico SDK. And inside of your project folder, you're going to have your C file, the CMakes list text file, we talked about that, and the Pico SDK import CMake. So you can grab these from the Pico examples folder, and then you'll create a build folder. You go into the build folder, you run CMake space ... to CMake what's above it, and then in the build folder it will create all the files you need, including your debugging files and of course the UF2 for programming. Yeah, so I found that was the best way to do it. Basically, edit the C file in a program, and then use the terminal to do CMake, just set it up, and then you run make from this folder to actually compile it, and then updates UF2, which you can drag over. Yeah, so maybe in the future I will experiment with SWD programming. I haven't found a tutorial on how to do it yet. They say you can debug with SWD, but I haven't seen how to program with it. Maybe someone has done it. Leave a comment below. In conclusion, setting up C programming on the Raspberry Pi itself is a little easier than Windows, but probably still not as easy as it should be. Obviously, I'm sure things will, mature as time goes by. This is still a very new microcontroller. For now, I still think the killer app is using MicroPython, because yeah, you just drag one file over and then you can use Thonny, which is easy to use on Windows. It's included with the Raspberry Pi, although as you saw, I had to update Thonny in order to have the Pi Pico support. The thing that's nice about MicroPython is that you can basically immediately upload changes. You don't have to push the button. You don't have to unplug the Pi Pico. It basically just works. And then, of course, if you want to make it boot to that program, you just call it main.py and save it to the Pi's flash memory. So we'll see if the C infrastructure improves, but I still think the best case use for this right now is probably educational purposes with MicroPython. For myself, I would probably still just use like a off-the-shelf ARM Cortex M0 because it's going to have a much more mature ecosystem behind it. And there are some things about the Pi Pico that I think, even though it has a lot of RAM, which I'm sure was to facilitate MicroPython, it has a lot of RAM and it has those PIO, programmable peripherals. However, there's other things that seem limiting, like it only has 2 UARTs, 2 SPIs, and 2 I2Cs, whereas other Cortex M0s, you have pretty much every pin is assigned to what's called a SIRCOM, and you can configure them to be whatever you want. UART, SPI, and then you can mix and match. So you could have 20 UARTs if you wanted, or 5 SPIs, and 2 UARTs, and 3 I2Cs, and it's all very configurable. And so this chip seems a little bit more limited in that capacity. And yes, you can program the PIOs to do that sort of thing. But again, that's an emerging technology. So this chip, more and more, the more I think about it, reminds me of the Parallax Propeller, which is coincidental because I actually do have a Parallax Propeller 2 now, and I'll be making a video about that in the future.
Cute.